Hi everyone, today we are going to be discussing the next generation science standards. As we discussed previously, the next generation science standards are the science standards that are used across the United States. And almost every single state has adopted the next generation science standards to their own. So for example, here in Louisiana, the Louisiana Science Standards are almost identical or very similar to these next generation science standards. So what exactly are the next generation science standards? Next generation science standards are made up of three dimensions: practices, core ideas, and cross-cutting concepts. It rests on a view of science as both body of knowledge and an evidence-based model and theory building enterprise, or that students are actually going to do science and not just listen, read, and watch about science. They continually extend, refine, and revise knowledge just like we do in science, and it presents three dimensions that will be combined to form each standard. So you will see these three standards, practices, core ideas, and cross-cutting concepts, in every single science subject that you teach. So let's look at a Louisiana State Science Standard. Here we're looking at a high school physical science standard, HS-PS1-1. And the standard itself, or the performance expectation, is use the periodic table as a model to predict properties of elements based on the pattern of electrons in the outermost energy level and the composition of the nucleus of atoms. Now, for some of our teachers, you might be a little rusty on chemistry, or maybe this is the first year you're teaching chemistry and you normally teach biology or environmental science. Therefore, there's always a clarification statement for teachers. In this case, the clarification statement focuses on both physical science and on chemistry. So let's talk about chemistry first. Examples of properties that could be predicted from patterns could include reactivity of metals, types of bonds formed, number of bonds formed, atomic radius, atomic mass, or reactions with oxygen. Many of these concepts we learn when we're learning about the various trends on the periodic table. Additionally, they also have a clarification statement for physical science. Examples of properties that could be predicted from pattern could include metals, nonmetals, metalloids, number of valence electrons, and types of bonds formed or atomic mass, with emphasis on the main group elements. Then you will notice that there are the three different dimensions within the standard. You see a science and engineering practice, and you see one that is bolded out of 8. Then you see a disciplinary core idea and a cross-cutting concept. We are going to deep dive into each of these, but what I'd like you to think of now is the science and engineering practice is what we want our students to do when we tackle this Louisiana State Standard. And the disciplinary core idea is what we want our students to learn. What we want our students to understand is the disciplinary core idea. And the cross-cutting concept is something that these students could apply between various scientific disciplines and maybe even other subject disciplines altogether. So we're going to get started by discussing the science and engineering practices first. When we are describing science and engineering practices, we are describing behaviors that scientists engage in as they investigate and build models and theories about the natural world. This is how we want our students to engage with the science, or this is what we want our students to be able to do. There are 8 different types of practices, and we're going to go over each one. Now, remember, there is only one scientific practice for each standard. However, what you are going to notice when you start looking at your curriculum is that throughout a unit or a year, your students will have the opportunity to practice all 8 science and engineering practices. So the first science and engineering practice, or SCP-1, is asking questions for science and defining problems for engineering. And what you'll notice is there are different expectations for middle school versus high school. And that's because we want to scaffold. there are certain things that we want to expect our middle school students to be able to do compared to our high school students. So, for example, in both middle school and high school, we expect our students to be able to ask questions and define a problem. However, the questions might look a little bit different. So, for example, we might want our students to be able to clarify and refine a model, an explanation, or an engineering problem in middle school. However, not only do we want that in high school, but we also want them to examine models or a theory to clarify or seek additional information and relationship, which is taking it to the next level. So when you're looking at the science and engineering practice, not only do you need to understand it, and asking questions and defining problems is a pretty basic science and engineering practice, no matter what age you're in, but you also have to be able to differentiate what is expected from a middle schooler versus a high schooler. So, for example, this is a great one. When students are learning physical science, you could present the phenomenon in which you ask what happens when a sharp object and a balloon come into contact. And then you could show them the balloon skewer lesson plan, or you could do that, where then students have to explain why didn't the balloon pop. And you could start asking them questions, and then maybe they could apply this particular scientific concept to a problem. Maybe that involves hot air balloons or blimps. The science engineering practice 2 is developing and using models. Now, if you are one of my current students, you know I'm really into models these days because we've started the molecular modeling library at Nichols State. And for the science engineering practice, what we want is for students to construct models as helpful tools for representing ideas and explanations. Now, sometimes, particularly in middle school, it gets a little bit overwhelming considering what kind of models we want our students to make. And maybe we reflect on our own models, like did you build a cell out of food or styrofoam? Or maybe you created a model of the solar system. Some models can be really simple, like drawings and diagrams. Others might be a little bit more like physical replicas. But also consider that mathematical representation, analogies, and computer simulations like PhET can also be considered models. Modeling tools are used to develop questions, predictions, and explanations. And models are used to build and revise scientific explanations. Many of our scripted curriculum these days have our students create a model early on to explain a natural phenomenon. Then, as students get more data, are presented more information, they continue to revise their model until they agree upon a model that will be their final explanation. You can see that between middle school and high school, there are some major differences when we're talking about modeling. For example, in middle school, we want our students to be able to evaluate limitations of a model for a proposed object or tool. However, in high school, not only do we want them to be able to do that, but also process, mechanism, or system in order to select or revise a model that best fits the evidence or design criteria. And we may even want our students to design a test of a model to ascertain its reliability. Additionally, we may expect our students to not only develop a model to generate data, but also allows for manipulation and testing of a proposed process or system. In Science and Engineering Practice 3 is planning and carrying out investigations. This is the one that we are most likely familiar with from our own experiences in K-12 science education. Students should have opportunities to plan and carry out several different kinds of investigations through their elementary, middle, and high school years. At all levels, they should engage in investigations that range from those structured by the teacher in order to expose an issue or question that they would be unlikely to explore on their own, for example, measuring specific properties of material, and also those that emerge from students' own questions. This is particularly important for our students who are coming from elementary and middle schools that have scripted curriculum. They may not have that opportunity to explore the questions they want to explore or design experiments. So here's an example. You do need to make sure you scaffold up the science and engineering practice by providing information on how a student should be able to plan an investigation. I would also recommend that you format a graphic organizer or lab report for these students so that they fully understand the type of data they need to record and how they are going to document the process of not only engaging in the investigation but collecting data from it. So again, you can see that there will be differences between middle school and high school when it comes to these ideas. For example, in middle school, we want them to conduct an investigation and or evaluate or revise experimental design to produce data to serve as the basis for evidence that meets the goals of the investigation. But in high school, not only do we want them to be able to conduct an investigation, we also want them to be able to plan and conduct an investigation or test a design solution in a safe and ethical manner, including considerations of environmental, social, and personal impacts. We also want our students to be able to select appropriate tools to collect, record, and analyze and evaluate data in high school, whereas in middle school, we may only want them to evaluate the accuracy of various methods for collecting data. In this case, what we're going to do is we're going to do experiments that students design. Great examples for this is having students design a science fair project, which is commonly done usually in 8th grade in our state. Additionally, you could do some fun things, like if you're teaching physical science or physics, you could have your students design various types of marshmallow catapults, and then they can figure out which design is best to get their marshmallow the furthest across the classroom or the gymnasium floor. In Science Engineering Practice 4, we want our students to be able to analyze and interpret data. Once collected, data must be presented in a form that can reveal any patterns and relationships and that allows results to be communicated to others. Because raw data as such has little meaning, a major practice of scientists is to organize and interpret data through tabulating, graphing, and statistical analysis. Now, in middle school, we're going to expect our students to be able to organize and graph the data, whereas in high school, we may consider applying more advanced graphing and statistics. This is a great video on how the practice of nature of science is used for analyzing and interpreting data, and I highly recommend that you watch it. So again, you can see that there are going to be differences between middle school and high school when coming to the science and engineering practice. In middle school, we may want our students to analyze and interpret data to determine similarities and differences in findings, whereas in high school, we want them to be able to compare and contrast various types of data sets to examine consistency of measurements and observations. This science and engineering practice is also commonly found on the LEAP exam, so I highly recommend that even if the standard that you are working in doesn't have the science and engineering practice, that you have them practice analyzing and interpreting data as much as possible. The next science and engineering practice is using mathematics and computational thinking. Now, using mathematics seems to make sense, right? There's a ton of math in science. However, the computational thinking can be a little bit more difficult. Students are expected to use mathematics to represent physical variables and their relationships and make quantitative predictions. Now, I give you an example of how to use mathematics and computational thinking using the PhET lab, in which it's the pendulum lab. But additionally, there are other explanations for this, and I highly recommend that you click on the hyperlinks in this presentation. When using mathematical and computational thinking in 6 through 8, it's going to build on what they've already learned in K through 5 in identifying patterns in large data sets and using mathematical concepts to support explanations and arguments. Now, when we get to high school, we're going to progress into thinking and analysis, a range of linear and nonlinear functions, including trigonometry, exponentials, logarithms, and computational tools for statistical analysis to analyze, represent, and model data. Simple computational simulations are created and used based on mathematical models of basic assumptions. These are great for ecology lessons, weather lessons, and physical science lessons where students might need to make predictions based on data that they have collected. For Science and Engineering Practice 6, we want our students to be able to construct explanations and design solutions. How many of us have heard the term CER, where they have to explain and elaborate using reasoning? Here we want to ask students to demonstrate their own understanding of the implications of a scientific idea by developing their own explanations of a phenomenon, whether based on observations they've made or models they've developed. We also want to engage them in an essential part of the process in which conceptual change can occur. So here we want them to be able to construct an explanation and design a solution to a problem. Here's an example. Maybe we want them to build a ring using Pringle chips. How could you do this? And then what's the explanation behind how you can actually do this and the chips don't just all fall? So again, there will be major differences between middle school and high school when it comes to this. In Science and Engineering Practice 7, we also want them to be able to engage in argument from evidence. So again, thinking about the LEAP exam and CERs, we want our students to be able to think about and be able to express their ideas and argue. In this case, when we talk about arguing, we're talking about a process for reaching agreements about explanations and design solutions. We don't want our students to fight each other, but we do want them to be able to have a productive discussion about their designs, their ideas for a solution or a model in a way where they can get other classmates to decide if they agree or disagree with them. In science, reasoning and argument based on evidence are essential in identifying the best explanation for a natural phenomenon. And in engineering, reasoning and argument are needed to identify the best solutions to design a problem. So, an example, you can have students identify parts of an argument. Remember I was talking about CERs, that's claim, evidence, and reasoning, which we see on the LEAP exam a lot. Well, what if you were to have them not only do claim, evidence, reasoning, but also rebuttal, where they can decide if they still agree or disagree with what they had come up with. And there's a lot of great examples out there, and there are terrific resources for this. I highly recommend that you take a look at the argumentation toolkit as well as the Sadler Science resource when you're thinking about how you're going to tackle the Science and Engineering Practice 7. And here's a great infographic on how you can create a productive argumentation activity. So again, we don't want our students yelling at each other. We're not thinking about this as a traditional argument, but what we do want is for our students to be able to express and stand up for, using evidence and reasoning, their ideas around a scientific phenomenon. And then finally, what I would consider to be one of the most important science and engineering practices for today is being able to obtain, evaluate, and communicate information. We want our students to be able to read, interpret, and produce scientific and technical text. What that means is we want our students to be able to speak and write science. We also want them to be critical consumers of information about science. What that means is I want your students to walk out of your classroom and be able to decipher what they saw on TikTok, Instagram, and Facebook as pseudoscience or real science. And if they can reason with understanding, is the data that we're learning about going to hold up in what I'm hearing on social media? We want our students to be able to be reading scientific texts that are adapted to the classroom. Make sure that the reading level is appropriate. And we also want them to be able to communicate technical information. This might be through both writing or oral presentations. And then in high school, what we want is for them not only to be able to speak and talk science, but also be able to graphically and mathematically communicate science as well. For those who are looking for a great resource on how to get our students to learn how to read science or scientific papers, AAAS's Science in the Classroom is a terrific resource which breaks down scientific papers and is annotated by high school students for high school students. So it's in a language that is understandable for everybody. Now that we've gotten through the science and engineering practices, let's discuss cross-cutting concepts, or CCC. Cross-cutting concepts have applications across all domains of science, and as such, they are a way for linking the different domains of science, so between biology, environmental science, chemistry, and physical science. These cross-cutting concepts include patterns, similarity and diversity, cause and effect, scale, proportion, and quantity, systems and system models, energy and matter, structure and function, stability, and change. Additionally, there are DCI groups. This is disciplinary core ideas. And depending if you're teaching middle school or high school, these are going to look a little bit differently. In middle school, in 7th and 8th grade, you might be teaching across all 4 domains, because in middle school, we teach a little bit of life science, earth and space sciences, physical science, and engineering. However, in high school, you will majority teach only one subject. So you may be teaching biology, chemistry, physical science, or maybe you're teaching a STEAM or STEM course where there's going to be engineering also in the coursework. Disciplinary core ideas have the power to focus science curriculum, instruction, and assessment. Remember backwards design. This is your objective. This is what I want my students to learn. So if you know that, then you can build the assessment and then identify the activity or the material that is going to help your students learn that information. They usually have broad importance across multiple sciences and provide a key tool for understanding or investigating more complex ideas. They also relate to the interests and life experiences of your students. Remember, on the NIET rubric, that motivation piece, this is where it all connects. And be teachable and learnable over multiple grades. What you will find is your students have already been exposed to almost every single disciplinary core idea you are teaching to some level in both elementary and in middle school. So to summarize, if you need a video that's going to show you how things are explained a little bit differently, I highly recommend that you check out this video from Bozeman Science, and he has terrific resources on how to break down the next generation science standards in general. Now let's go back to that Louisiana State Standard I opened this lecture up, that HS-PS1-1. Where we want our students to use a periodic table as a model to predict the relative properties of elements based on the patterns of electrons in the outermost energy level and the composition of nucleus of atoms. The science and engineering practice that this Louisiana State Standard wants us to tackle is developing and using models. Specifically, modeling in 9 through 12 builds on K-8 experiences and progressing to using and synthesizing and developing models to predict and show relationships among variables between systems and their components in the natural and designed worlds. We want our students to be able to develop, revise, and use model based on evidence to illustrate and or predict the relationships between systems, between components of the system. So in this case, we want our students to be able to develop models about these elements and how they interact with one another involving the electrons. Now additionally, what we actually want our students to learn is that each atom has a charged substructure consisting of a nucleus, which is made of protons and neutrons surrounded by electrons, and that the periodic table orders elements horizontally by the number of protons in the atom's nucleus and places those with similar chemical properties in columns with repeating patterns of this table reflects patterns of the outer electron states. So we're basically going to be teaching students how the periodic table is organized and more specifically how we are going to model elements with what is consistent in the nucleus and then about those outer valence electrons. And finally, we're going to look at the cross-cutting concept. In this case, we're looking at patterns. We're looking at different patterns may be observed at each of the scales at which the system is studied. So in this case, we might look at patterns between the elements. How many atoms do you have, and what does that mean? Not how many atoms, excuse me. How many protons and neutrons do you have? How many electrons do you have? And then also looking at how patterns are related on the periodic table and what that means as well. So what we're going to do is we're actually going to break down the Louisiana State Standards that we are teaching using this knowledge of three-dimensional science teaching for this semester.